Hello, we're still talking about energy changes and chemical reactions, particularly reactions involving covalent molecules, and we're talking about the breaking and making of bonds in this particular video. And so let's define a term that is what we're going to call the bond enthalpy. And it's the enthalpy change associated with breaking a bond in 1 mole of gaseous molecules. So it's defined as the breaking of bonds and how much energy is going to be required to do that. So the breaking of bonds, you got to put energy in the molecule. It's always an endothermic process. It's going to be a positive number. We've got to add energy to break that bond. Whereas the making of bonds always releases energy. It's going to be an exothermic process. That delta H will be negative. So breaking requires making releases energy. And so let's use Hess's law. So the change of the enthalpy of the reaction is equal to the change in enthalpy of breaking bonds plus the change in enthalpy of making bonds. And so that understanding that's very, very important. So this enthalpy, bond enthalpy, since that quantity is defined in terms of breaking bonds, that's always going to be a positive number. Which means, going back to the way we use thermochemical equations, if we were to talk about bond enthalpy in terms of making bonds, that has to be the reverse energy. Same magnitude, opposite sign. So, the equation we're going to use to calculate the enthalpy change for a gas phase reaction is that the change in enthalpy, delta H superscript 0, is equal to sigma summation the bond energy of the reactants minus the summation of the bond energy of the products. So this is reactants minus products. So you said, oh, he's always said it's always final minus initial when we're looking at changes. Products minus reactants. But this is different. This is using Hess's law. We're adding, breaking, and making. And so to make this work out, making bonds is the reverse. It's negative. And so that's the way this reaction comes out to be. It's the summation of the bond energy of the reactants minus the summation of the bond energy of the products. It's all because we're using Hess's law and the way we define bond enthalpy. So make sure you've got your head wrapped around that. And don't let this equation lead you astray. So here's our equation again. And so this delta H0 is equal to total energy input to break bonds minus the total energy released when we're making bonds. And it's negative because we had to change the sign because of their definition of bond enthalpy. So bonds broken minus bonds formed. That's what our delta H0 is going to be in terms of enthalpy. And so if we look at a simple case, the diatomic molecular hydrogen, we got to add 463.4 kilojoules per mole to atomize it, to break it apart into its constituent atoms. Likewise, if we were to do the opposite process, to take 2 hydrogen atoms and put them together, they're going to release energy. And how much energy will they be releasing? It's going to be minus 436.4 kilojoules. And so here's a table of bond enthalpies. You'll notice that they're all positive, and they're all positive because of the way we define bond enthalpy is the energy required to break a bond. The diatomic molecules are in red. These values can be exactly known. The ones in black are approximations. For example, the hydrogen-oxygen bond is 460 kilojoules per mole. That's an average of the different types of hydrogen-oxygen bonds we can have. It can be the oxygen-hydrogen bond in water, or an alcohol, or carboxylic acid, and any combinations of those. So what scientists, chemists have done is they've taken some number of those different molecules and taken the average of those to come up with these. One note, look at carbon-oxygen double bond. And so a carbon-oxygen double bond in a molecule other than in carbon dioxide is 745 kilojoules per mole. If you're looking at carbon dioxide, it's now 799 kilojoules per mole. Because you've got two C double bond O's in that particular molecule. It's a very small molecule, and we can determine that exactly. Whereas the C double bond O, that's the average of different molecules with a C double bond O in it. So bond enthalpies are always positive. So we can use them to make estimates of the enthalpy of reactions for different substances. And so let's take methane, CH4. Let's combust it, burn it with oxygen, make carbon dioxide and water. So 1 mole of methane plus 2 moles of oxygen combust to make 1 mole of carbon dioxide and 2 moles of water. So we have a short abbreviated table to look at. And so what we need to do is add up all the bond energies for the reactants and subtract all the bond energy of the products. But to do that, we need to make sure we know what types of bonds we're looking at. So what we're going to do is let's look at the Lewis structures and determine which bonds are to be broken and which bonds are to be formed. And so here's our reaction. There's our methane, our tetrahedral methane with its 4 CH bonds, plus 2 molecular oxygens, each with a oxygen-oxygen double bond, react to make carbon dioxide that has 2 carbon-oxygen double bonds, plus 2 water molecules, with each one of those having 2 oxygen-hydrogen bonds. And so we can use our table off to the right. We're breaking 4 CH bonds and 2 oxygen-oxygen double bonds. We're making 2 carbon-oxygen double bonds and 4 hydrogen-oxygen single bonds. So we're using the table, so 4 times 414 kilojoules per mole for CH bonds, plus 2 times 498.7 kilojoules per mole from our oxygen-oxygen double bonds. So that's summing up the bond energy of the reactants. Now we're going to subtract the bond energy of the products. We got to subtract because the way we define bond enthalpies is always as breaking them, and those numbers are positive, but now we're making bonds, so we got to use the reverse sign here, and hence we're going to do that by putting a minus sign in this equation. We've got 2 carbon-oxygen double bonds that are in carbon dioxide. So that's the little footnote at the bottom table. So they're each worth 799 kilojoules per mole. We got 4 hydrogen-oxygen bonds at 460 kilojoules per mole. Do all that addition, all that subtraction, and we wind up with minus 785 kilojoules per mole. So graphically, we can look at this. Let's look at the reaction of molecular hydrogen plus molecular chlorine to make hydrogen chloride gas. Turns out it's an exothermic process. What that means is we're releasing energy. What that means is our products have less energy than what our reactants have. And so if we look at this, we got this y-axis, vertical axis of energy, and you might sort of think of the horizontal axis of being time. So we're starting out with the reactants. We've got to put in energy, bond enthalpy positives to atomize, to break those molecules apart, and then there's a release of energy as we make our molecules. And these particular molecules have less energy than the reactants. So it's a negative delta H0, and hence it's an exothermic reaction. Whereas, if we take ammonia and decompose it, into its constituents of molecular nitrogen and molecular hydrogen, we got these reactant molecules that are ammonia. We're adding energy to atomize, to break them apart. And then we're making new molecules, we're making new bonds. And so here the reactant molecules were lower energy than the product molecules. And so there's been the product molecules have higher energy. So this is endothermic process. We've got a met process. We've had to add energy to make this happen. Thanks for watching.